Okay, today we're going to talk about the ladder of powers, and those are nonlinear scatter plots and using the power transformation ladder to straighten out data. And we want to be able to take data that is not straight and try and make a linear model out of it. It's kind of hard to do, but once you get the hang of it, it's not too difficult. So previously, when we've been looking at the linear regressions, what we've found is that we always get a nice straight model. These data points are nice and straight. However, now we're going to be looking at models that are not necessarily straight, that are curved or that are nonlinear. Also, throughout this video, you might see some writing here. You can feel free to pause the video if you want to read through those words. Often I'll be going over those words, but if you want to pause, go ahead. But again, what will happen here in these things is you can't see this curve in the relationship. Sometimes the curve hides. It looks straight, but it isn't. But you have to plot the residuals to see the bend and the pattern in the residuals. So earlier we did a problem where we talked about the weights of cars and the mileage, the weight of the car versus the fuel efficiency, like miles per gallon went down as the weight of the car went up. Okay, now when you look at this, it looks pretty straight. It looks like this thing's pretty straight. So we ran a linear model and we got this regression model. And here's our linear model for this relationship. It looks pretty strong. It's got a good R, a good correlation coefficient, and you can interpret these coefficients. You know how to interpret the y-intercept and the slope. So I'm not going to get into that right now, but if you want to, you can pause the video and write down your interpretations for those as well. Now, when we ran the residual plot of this, what we ended up seeing was a sort of pattern in the residuals. And because I saw this sort of up and down and then back up pattern, what I find is that this linear model is probably not appropriate for this relationship. That doesn't mean we're out of luck, and that doesn't mean we're doomed. We can do something about this. So because the residuals should have no pattern, and we saw a pattern, then it's true that the model is no good. Okay, so remember, the residual plot will show patterns that are really difficult to see in the original scatter plot. On to the next. So one of the ways we might try and correct this deficiency is to re-express one of our variables. Now, instead of looking at miles per gallon, we're going to do what the rest of the world does and look at the number of gallons per mile. Actually, most places they would look at gallons per 100 miles, but in Japan and most countries, they look at liters per 100 kilometers. Okay, since we're working in the American system, we'll just stick with gallons per 100 miles. So for example, if you have 35 miles to the gallon here, if I wanted to convert that, I would have to multiply by 1 gallon over 35 miles, which is what we have, because I want to convert to gallons per mile. Then I would multiply that by 100 divided by 35. Now that's just as easy as dividing 100 divided by 35 and getting an answer, and that's the number of gallons it takes for 100 miles. Okay, if I'm using unit cancellations a la chemistry, then this is what I end up with, and I end up with gallons per 100 miles. Now, when I plot that, gallons per 100 miles here, if I put gallons per 100 mile, or excuse me, weight here and gallons per 100 miles here, then what we see is a much straighter, nicer linear regression. And when we do the residual plot, we see a much better random scatter here. Okay, it's not a pattern, so we're good here. So the bottom line is, by re-expressing our data, we were able to straighten out the model, create a better linear model, and something that we could actually do realistic predictions for, or realistic interpolations for, as opposed to a model that may not be as efficient or as good. Let's go ahead and pause the video and read through this problem. So it makes sense. In other words, in a river, basically, the current will go faster in the middle and slower on the edges, and so they're going to examine a bunch of data and see if you can create a model for the further away you are from shore, is the current going to actually go faster as you would expect. So what I'd like you to do now is to pause the video, load this data into your TI Nspire and go ahead and graph it. And then once you have your scatter plot, run your linear regression and see if you can check the residual plot and see anything distinctive. So go ahead and pause the video and do that, and then we'll move forward from there. Okay, so we ran the residuals, we ran the linear model, and we got a nice R squared. We have a nice model here. But when we ran the residual plot, we also saw this sort of up and down pattern. Okay, so we need to think about what can we do to make this more straight. Now, right now we're just guessing. So because we're just guessing and we don't have a system in place to kind of figure out how to re-express this data, I'm just going to guess. Okay, so what I'm going to guess is I'm going to guess that if I made x's smaller, then this might squeeze these values to make a tighter model, a more linear model. So I'm going to squeeze the x's by square rooting the x. So what we're going to do is we're going to re-express our distances as the square root of the distance, and we're going to graph the square root of the distance against the velocity. So we'll be using a model that's going to be the square root of the distance versus velocity. You can go ahead and do this on your spreadsheet by on the TI Inspire by using the formula function equals the square root of whatever distance is. Okay, and then just call this square root distance. Now once you have that done, you can go ahead and plot that and do a linear regression and see what you come up with. See if you can come up with anything distinctive. Okay, we actually got a higher R squared value here. This R squared value is higher. We still have a tighter model a little bit, and our residual plot is more random scattered. This sort of tails off at the end. It looks kind of like a pattern, but I think this is much better than our previous residual plot and is really more random and scattered. Okay, so what we have here is a random scattered residual plot and a much better, tighter model. So velocity hat, if you wanted to call it velocity hat, equals 3.01 times square root of distance plus 20.1. Now it's probably better to write this the other way, a plus bx, but this is the way it's printed down here, so I'm going to leave it in that form, but normally we'll write it 20.1 plus 3.01 times the square root of distance. So if I wanted to predict something based on the distance from the bank, I would actually plug in the distance, square root it, multiply it by 3, and add 20.1 to get the velocity. Okay, so it looks like it worked pretty well, and trying to figure out what to do here, this ladder of powers has provided some good guidance to statistics folks to figure out what to do. So you want to visualize this as a ladder, okay? And we'll talk about this on the next slide, but basically this is the power of 0. This is nothing happening, or the power of 1, I should say. And then if you go down the ladder of powers, you're going down in powers, you're going up in powers. So think of it as crawling up the ladder to make your x or y bigger, going down to make your x or y smaller. And here's the ladder of powers and what it looks like. So this would be like our ladder, and you visualize that you're standing here at this place where you're not doing any transformation. If you want to make x smaller, you go down the ladder of powers 1, 2, 3 like this. You would do some sort of transformation down, like square root, cube root, log, or reciprocal of the original value, whether it's y or x. Then to go up, you would square or cube it or raise it to the fifth root, or raise it to the fifth power, etc., etc. So you visualize that you're starting here, and you're either going down this way or you're going up this way on the ladder of powers. So we've already looked at like multiplying by something, like by 100, or multiplying by something. We've also looked at the square root. Okay, we looked at the square root of x as a transformation. Okay, and now we're going to take a look at what we have to do based on the look of the graph. So there's going to be 4 basic shapes And each of these curved scatter plots are going to tell you exactly what to try and transform your data into a straighter model. Now look here, and basically what you have is, you can pause the video if you want to look at it, but each of these curves represents a shape of data. For example, this plot right here, number 2, this is the shape of what you see when you run your scatter plot. So if I had a scatter plot that looked like this, curved like this, then what I would be expecting to see is a curved scatter plot that's going up like this. And now what I need to do is based on what I see here with the X and Y, right? So this curve fits right here. So I would be trying to go down on the Y or up on the X. So in other words, one of the things that's nice to try when you have some sort of curve like that is to square root Y or log Y. And that usually works pretty well to straighten out a curved set of data. Okay, so if you had a curve that looked like 3, which looks like this, then you would go down on the Y, meaning you would log Y, square root Y, something like that along that ladder of powers slide. Or you would go down on the Y, or X. So down on the Y, down on the X. If your curve looked like this, you would go up on the X. In other words, you'd square X, cube X, raise X to the 5th power, and up on the Y. Square Y, square X, etc. Square Y, cube Y, etc., etc. This kind of curve will get straightened out by doing that. Okay, and over here on 4, what you have is you'll go down on the X and up on the Y. So you'd square Y, cube Y, or log X, or 1 over X, or square root X, or something like that to try and make this straight. And you have to try, sometimes you have to try multiple things to try and get that done. So read the problem, have a pause, and see if you can figure out what you'd do. Again, have a read, and you can see it's really simple just to look at the model and figure out where it is. I draw it as a bullseye. I do this just to visualize it, okay? Okay, and this makes me remember, okay, this shape of a curve here, this shape of a curve tells me to go up on the X and down on the Y. This shape of curve here, for example, tells me to go up on the Y and down on the X, etc., etc. Go ahead and plot this on your calculator and see if you can figure out a way to straighten it out. Okay, so if you look before transformation here, what I've done is just basically done a scatter plot of the raw data. And if you look at here, after logging the acres, what has happened is, but because this shape was curved like so, what that told me is that if you think about it, remember that this is what it looked like, right? So this means that, I'm going to go down on the Y, okay, or up on the X. So remember that this curve shape like this tells me to go down on the Y or up on the X. When I see a curve that looks sort of exponential, logging is a good thing to do. So I logged the Y, which takes down on the Y, it takes the value from really big to a reasonable small size, and has then straightened it out. Now, if you run the linear model, you'll see that the residuals and everything else also work out. So logging Y here is a good transformation. So here's a question. Predict the acres that are defoliated in 1982 using your transform model. I'll leave the answer to you, but it involves unlogging the Y. In other words, you have to take 10 to the whatever the value is equals Y. Okay, so you got 2 problems to do here, and what you can do is go to EDSB, and if you open up under EDSB, under Unit 2, Exploring Relationships in the library, there's a TI Inspires Files folder, and in there you'll find one of the problems says Re-expression Chapter 9, Numbers, and that's actually Numbers 16, and also the next slide, also it's 2 book problems. So if you'll go ahead and do that, you can download the data and play with these things and see if you can answer them. It might involve more than one transformation, but give it a whirl, and I'll answer any questions you have next time. Here's problem 2. It's number 17. So again, this will be in tab 1.2. It'll have the list of the players and all their salaries. See if you can play with this and come up with a scatter plot, and then see if you can re-express the scatter plot so that it makes sense and you can use a linear model with it. Once you're finished with these problems and you understand both of them and you're good to go, what I'd like you to do is either work on homework, or you can work on your projects. Okay, so you can work on homework or you can work on the projects. Thanks, and have a great day.